Okay, my friends, I am doing a little MATLAB demo here on the Zoom for recording for you. I don't have notes. I'm doing it off the cuff. I thought it might be more interesting. We'll just see where it goes. The idea, though, for sure, what I want to cover is basic commands like how to put a matrix into the software, how to put a matrix into MATLAB, how to multiply, how to find the inverse, how to solve a system, how to solve a least squares equation, how to project, how to find a projection matrix, how to project a vector onto a subspace, how to find the rank. These are the things. Yeah, and then we'll test some of the properties of determinants, how to find the determinant, the null space. So I should probably make a list. I'll keep a list as we think of things. And we'll have another one for eigenvalues next week. So let me share the screen here. Yeah. So I don't think, well, let's see. Okay, yeah. One thing is I'm using Octave. You can see how I'm using a pretty old version of it too, but it works. You should be using MATLAB from making the installation from MathWorks using the Clark account. Okay, so you see I was experimenting here with some commands that I haven't used in a while. Let's try to just make do a simple thing from maybe the first part of the course. Let's just see, how would I just enter in by hand a matrix? Now, there are ways to enter in matrices from files and things like that. We don't need all those tricks because we're just learning linear algebra, and most of our examples are pretty small. But you can see, remember, even when we do least squares and we have rank 3, we end up having to do an inverse of a 3 by 3 matrix. That's already too much, right? And to do by hand many times now. Now you can actually feel free to put in bigger systems and you don't have to sweat that. All right, so let's suppose, yeah, we just want to enter in something by hand. Then the default way is with a square bracket and spaces or commas to separate the numbers. I don't want to put anything too weird in, so let's just do something like this. So row 1, row 2, and let's make another. Okay, now suppose, I was thinking in columns, then you can just take the transpose. You can say A equals A transpose. Now that I just forgot to put I did forget, I missed. There, that's the transpose, is the apostrophe. You can also write the word transpose and put A in a. Okay, so now A is it's flipped. A is flipped. If I want to go back, I could just, if I just type A transpose, it just gives me A transpose. It didn't set A though. A is still like columns. You could also say, if we just want to see the transpose this way, I think you don't have to complete the word. Yeah, but A is still this. So, all right, that's reasonable. What do you think the rank of A is? 3, right? Yes. You just made that up. It'd be very strange if it weren't 3. Now, what's a projection matrix that projects onto R4? Projects vectors in R4 onto the column space of A. Call it P, you can call it whatever you want. It's your session. A times inverse A prime, A transpose times A, right, times A transpose. Yeah, I suppose so. Okay, so there it is. You can see it's symmetric, 0.009, 7087. It's the same in column 1, row 2, or column 2, row 1. There's other ones that are the same too. Kind of interesting. There's a command now too that will give you the rational form of a matrix or a vector or a number called rats, and that's kind of nice. Hard to do by hand, and we get the full rational form. Very, very interesting, right? What's p squared? P squared should be pretty close to p, right? Let's see. See? P squared's p. Idempotency in the projection matrix. Okay, everything looks good. This is still relatively small, but the power is MATLAB doesn't care if you give it, you know, an 11 by 14 matrix. So we'll do one like that toward the end. All right, any questions? Well, I can't answer anyway because you're not in this meeting, but you let me know if you have questions. So let's actually solve a least square system. So say we have A here. Suppose I want B equal to something in R4. I'm going to guess something in R4 that I think is not in the subspace here. I have no idea though. Might be. Probably isn't though. R4 is so much bigger than this three-dimensional subspace. So there's B. And if I try, I could say X equals A slash B. It worked. Let's see, null A. What? Okay, so let's take X. I wonder if that is that the least square solution, or say A times X. Oh, it just gave me the least square solution. Yes. Okay, so it did the least square. So let's see if we get the same least square solution. Now let me slow down if you weren't following up to here. So I just made up that vector B1010. I didn't make this problem up ahead of time or anything. I'm just made it up, and assuming that it would not be in the span of the column space of A. It would not be in the column space of A. There's A. And then I use the backslash to solve A, B. So let's see, X equals A. Sometimes I get confused with these. Yeah, no, I had it right. So I think it gave me the least square solution. In other words, yes, it gave me the best it could, right? It did the least square solution. So let's actually see if we get the same thing by projecting B onto the column space of A and then solving. So take, actually that wouldn't prove it exactly, would it? Let's see. Let's do A times X, right? And then compare it to, that's A times X. That's not B, right? You see it's very close, but it's not B. So there's your error vector. E is equal B minus A times X. And I'm sorry. Yeah, sorry. Too much probability. Yeah, there's your error vector. Pretty good, pretty small error, right? Pretty small. It got us pretty close. Okay, now suppose we just do it by hand. We don't use the forward slash to give us the least squares, but that's cool that you know now how to do that, and that I do, that I remember. So we could say, we first project B maybe. So we could say, let's call it little p equals P times B, right? And that should be the projection. Yes, and there you have it. You can see above A times X. minus p should be basically 0. Yes. So one thing is, here was the error vector, right? Here was a times x. A times x can equal b because b is not in the column space of a. But it's equal to little p, right? The projection of b onto the column space. So, and that x was found by MATLAB using the same method that we just used. Okay, one thing to notice, this is 0 here, this last vector here. By the way, you see MATLAB automatically assigns a variable to your last command that you entered when you don't suppress the output, because it says if you didn't assign a variable to it, it will assign one for you, so for quick use, so you don't have to repeat the command. So we could work with ants now. So ants is that. If I type norm of ants, it will give me the 2D norm, Euclidean norm, called it's the square root of the sum of the squares. It should be pretty small, right? Yeah. So it's not actually 0. Why do you think? This is the big difference, the huge difference, and really the main reason one of the main reasons to make sure you do this and use the computer. You need to see that in the real world. Start with a little book problem like this. So it's not exactly a book problem, but a pretty small problem, right? Where were we? Where do we start here? Yeah, A is this matrix. It's reasonable. It's like something I would have on the homework. You're trying to say solve AX equals B. B was 1, 0, 1, 0. Not in the column space, so we need the least squares solution. So it's very reasonable. But then you actually find the solution, and it's not exactly B, right? It's close, but it's not exactly B. AX minus B, sorry, it's not, sorry. It's, sorry, P times B is not exactly AX, right? So there's a little round off error. So you get something very small, but theoretically everything was correct. It's just that these are irrational numbers. Sorry. They're definitely rational here in this matrix, but they're not exact, right? They're yeah. This is too many digits. You're not going to get this exactly, right? Infinite digits here. So repeats forever. So the problem is that at some point the computer has to cut off the representation. You get a little tiny error, propagates 10 to the minus 16, very small though. So okay, let's see. Let's do another one like this, just to emphasize this. So suppose we take another one. Now, suppose I want to make this up and I don't want to fuss by typing in the numbers. I can use the rand command to give me random numbers. So suppose I have A equals rand, move this, and I can specify to rand a big matrix of random numbers. So let's make it have something like, we want more rows than columns. So let's make it a little more interesting, 9 and say, I don't know, 13. Okay, so we have a 9 rows, 13 columns. Actually, since we're here, we can just tell it what we need. We don't, since we're not entering it in by hand, just tell it what we need. Let's make it 13 by, let's make it to 7. And let's suppress there. Okay, if I didn't suppress, it would dump everything out to the screen. Now I can look at A. Let's just look at one of A. If I want to just look at one single entry, say the first one, I could just do something like this. I could even look at the whole first column. Well, if I want to look at the first entry, maybe I do that. 0.04. Okay, yes. These are random between 0 and 1. If I want to look at the whole first column, I can type A. First column, let's see, means all rows. So you use the colon, full colon, to mean all, and then you put in which column you want. Let's put column 1 so we can see that entry again. Yeah, see, there it is at the top, and it dumps the whole column. Well, these numbers are all between 0 and 1. That's fine. It's a little easier to look if they're a little bigger. So let's just make them say between -5 and 5, something like that. So let's take A and multiply it by 10 and subtract 5 from it. So let's say A equals 10 times A minus 5. Now, minus 5 doesn't really make sense. So you've got to, but I think it will work. Yeah, it did work. It understands that you want to subtract 5 from everything because it doesn't make sense, right, to subtract a number from a matrix. So if we were doing it, the proper way to write it is -5 times the matrix of 1s, right? So if you're subtracting everything, 5 from everything, you want to subtract it from a matrix of 1s. By the way, I think there is a command called 1s, and let's see. A is, again, 13 by 7, right? So let's see what we get. We go 1s, 13 by 7. Yeah. Okay, so it did that. It's just, MATLAB helps you out. You know, it knows that you're busy, you're focused on the math. It tries to give you nice shortcuts to not bog you down with minor programming details. Okay, so now I've put A between -5 and 5. I would like to maybe round it so that I'm not looking at all those. So let's see what we get if we type round A. Yeah, that's nice, right? So let's have A equal ants now. Okay, now if I type A, A is assigned to this matrix. Okay. Well, let's repeat. Okay, let's take a vector in R13 and find the least square solution for it. So let's have B equal, we could take something pretty easy here. You could do a random B in R13, something like that, or we could just take something pretty easy, like we could do this trick. You could go B equals 0s and now make it be 13 by 1. Okay, and now we don't want it all 0, so let's make B 1 equal to 5 and B 1 5 6 equal to 10. Oh, sorry. B1, I did put a colon in by accident. That's okay. Let's just start over. That is one nice thing, right? You can just overwrite. Okay, there's B, and now let's have B 1 5 equal 3 or 4. Oh, God, I did it again. I put 1 through 5. Well, we learned something else, right? You can do this. And now let's have B1, this is what I meant, 2 equal 0, something like that. Oh, my God. Colon. All right, let's start again. All right, now, I just want to set like 2 of them non-zero. So let have B 1 semicolon No, row 1. Actually, it's a vector. I think I just do this. Yes. And B, let's say 4. Okay, there we go. That's maybe good enough. What the hell? So now, remember, we have A and we have B. Do you think B is in the column space of A? I doubt it. Let's see the rank of A. You can use the rank command. Rank of A is 7, full rank. Very nice, very nice, very nice. Do you think B is in the column space? I don't know. Let's see what we get if we go AX equals B. So if I want to solve this now, I have X equals A, B. That's the solution. Okay, that's probably the least square solution and not an exact solution. Now, how do we know? Type A times X and see if you get B. You probably won't. You're probably going to get P, the closest vector in the column space to B. So let's take A times X. Right. That's not B, right? Now B was 4. Remember, B was 4, 0, 0, 4, and then all zeros. You can see it does a pretty good job trying. It's got those 2s, 2.3 and 2.7 in the locations where there were 4s. So the 2 biggest entries are there. And the other ones are pretty small, but not that small. So like say we take now this ants, take the norm, will give me the square root of the sum of the squares of ants minus, now that's the projection, ants minus B. Wow, off by a bit, right? But it makes sense. You're in this big 13-dimensional space, and you're trying to find the distance to a 7-dimensional subspace of that space. And these were just typed in randomly. It could be a huge number. So it did the best it could, and you're still 3.4478 units away. Now, remember the projection matrix P is equal to A, what is it? A transpose, A times inverse, A transpose times A. You don't need to put spaces. I don't know, sometimes I do and sometimes I don't. It's up to you. There's the projection matrix. Ooh, I meant to suppress it. Well, there it is in all its glory. Let's get out of here. Okay. If you suppress it, it doesn't do that. Okay. Still computes, it doesn't do that. So that's P. If I type P times B, I expect to get that vector up there, that AX. Okay, so let's check. Let's call this little p equals P times B. So let's suppress it. And now let's compare AX. Let's take the difference here. So our error function then is B, no, this is not the same error. This is just checking to see if everything went right. So let's just see what AX, A times X. Yeah, minus, now it should be the same theoretically, but I expect some round off error, okay? Because we did it 2 different ways. Yeah, see, it's very good. You even get some actually some zeros in there. And anything below 10 to the minus, on this, with this software, 10 to the minus, I think the cutoff is around there, like 10 to the minus 14, 10 to the minus 13 is 0 pretty much. I remember how to compute that actually, but I'm not sure anymore on this computer. This is my secondary computer, my older computer. Don't remember. So let's see. What else could we do here? You want to do some more? What else could we do? Lots more we can do. I wanted just to make sure you could do all the basic stuff. Let's see. You could do, there's a command rank of A, I think we did this already. 7, right? Yeah, we did that. Null of A should give me a basis for the null space of A. It didn't work. Yeah. Oh, right. Yeah. No, it's not. It doesn't. It's full rank, right, in the column. So the left null space, if I do null A transpose, right, this will have how many dimensions? 6, right? 6 basis vectors. Yeah, I expected that to take a while. Yeah, look, there they are. So it normalizes them if I want to. So you see, I mean, I can't tell. We could put any one of these in now. Let's quit here and let's set this equal to something like this is a matrix, right? Let's call it NU equals ants. Oh, I did it again. Okay, so we have NU now. Okay. And if I take NU, A times any, actually, if I take A times NU, what do I get? I should get a 0 matrix, right? So A times NU. Oh, right, this is A transpose. So if I take A transpose times NU, there you go. So that's the 0 matrix. Does it look like all zeros? Yeah, it's all zeros. Okay, also it normalized it. If I take NU and I take, say, the norm of one of the columns, I should get 1. So norm of NU, and now I can just look at column, say 1. So that's all rows, use the colon, 1, should be near 1. It's 1. Okay, so what else? There's more we can do, right? We can now make an orthogonal projection of B onto Q, or I can find an orthogonal basis now for the column space of A. I can find a matrix Q, and then I can project B onto each column of Q and add those up, and I should get the projection of B onto A. Now, I don't know how long I've been going. Feels like a while. I think let's use a smaller matrix to do this little experiment with. Okay, so if you're still with me, let's reload a new matrix. So let's try to just do this again. And yeah, I wanted to do some stuff with determinants too, but I'm kind of thinking maybe we'll just do the orthogonal projection thing now, and then I'll do another one with determinants and eigenvectors. So let's let's make a new matrix A. So we could set A equal to again, let's do the rand thing. Let's make it 10 times rand, and let's not make it too big this time, and I'll round it to let's see, let's have it have say 5 rows and 3 columns. That's reasonable. That's annoying enough, right? To not want to deal with that. And let's have A equal round A. I don't even want to look right at. Okay, there's your A. Interesting, right? A couple 10s in there and some other. All right, what do you think the rank is of A? Good, 3, right? Makes sense. All right, so now suppose, yes, let's project some vector in R5 onto the column space of A. So let's have B equal, now I just make something up like, let's just take something like this, something very simple, like 2. And, okay, so B is a column vector in R5. And if I want to project it onto the column space of A, let's make P again, because we just want to demonstrate our lovely orthogonal theory. P is equal to A times A transpose, now I want the inverse of this, A transpose times A transpose. I don't even need to see it. Okay. All right. Now PB will be the projection, right? So little p equals PB. We can look at all these in a second. So. All right. And the error is B minus P. Let's look at it. Okay, there's some error, but we, again, three-dimensional subspace of R5. You have tens in there, right? And I'm trying to project this onto it. So there's some error there. So norm of E will give me the length of the error, 1.24. Okay, let's now do this another way. Let's see what P is. That's the projection. Okay. We could solve the least squares solution. Let's do that too. X equals A, B. That's the least squares solution. If I want to find X by solving using the P we just made, using the projection we just made, we would say X equals, watch, you'll get A, P, right? This should be the same thing. Same thing, right? I mean, we know P and B are not equal, right? P and B are not equal because they're E is B minus P, so this is the difference between them, but yet we get the same solution. It projected B into the column space of A and gave us P and solved that. It said, I can't solve you B, you're not in my space. I don't have a linear combination of these columns to make up U. Okay, so far so good. So let's now get an orthogonal basis for the column space of A. Now, this is Graham-Schmidt. There are other methods too. I will use just a command in MATLAB to do this. Now, on the homework, you're supposed to do it by hand. You should do it. You have to do it by hand, but you can certainly free to come check it if you want with this command. So say we take QR. Actually, it's a little funny. You put the what you want to save to on the left in brackets, and the commands are lowercase, case sensitive, and I can put the AN like this, and it should give me the following. Yeah. So one thing to notice, right? A was a 5x3 matrix. Q, this is giving me Q and R. I should have made them capitals because they're matrices, but I forgot. So this gives me Q and R. Notice Q is, now we know A equals QR. Q is 5x5 and R is 5x3. So we get a 5x3 matrix. What this did is it extended, it completed the basis to give me all of R5. So the first three are the ones that I want. That's an orthogonal basis for the column space of A. So it does this automatic extension for you for other applications that we won't get to until the second linear algebra course for data science. I'm just kidding, but I do think there should be a second. But let's take Q and let's just grab the first columns of little q. So let's have Q equal, let's see, do I know how to do this? Q equals little q, and I want columns 1 through 3, and I want all the rows. So I want all the rows, and I want columns 1 through 3, and this should give me the right thing for Q. I can throw away those other two columns. They're beautiful. It gives me a full basis, but this is all I want. And now let's call R equal little r, just so that we're, and what do you think? If I go QR, Q times R. Wait. What the hell? Right. Q is 5 by 5. Right. So I would have to also change R, right? I want to get rid of R. I want to get rid of those bottom two columns of R. So I want R equal, bottom two rows, R equals little r. I want to keep the first three rows. So I go 1 to 3. And that's it. I want all the columns. All those columns. Okay, there we go. All right, now let's try it. All right, that's 8, right? Yeah. All right, very good, very good. MATLAB works. Octave works. Okay, so let's now solve the least square system this way. So if I just want the least squares, remember we have AX equals B, right? And we're trying to find the least square solution. So we had X, the least square solution, is equal to, so remember, for the least square solution, let's call it X least squares, just so that we remember, is equal to A prime time inverse A prime times A times A prime times B, and that's the least square solution. XLS, let's see. Yes, I think that's the same thing MATLAB told us, right? Yes. Okay, now if I replace A with QR, what do I get? What do I get? Do it out by pencil. I would get inverse, right? Inverse. Let me put some inverse Q R transpose. So that would be R transpose Q transpose Q. I'm not using real MATLAB here, times R. And now times R transpose. Now I am using real MATLAB. So R transpose Q transpose B. Well, look, Q transpose Q is I. That goes bye-bye. R is invertible. So the inverse is flipped, right? So this is equal to, Q transpose Q is bye-bye. So I get inverse R times inverse R prime times R prime times Q transpose times B. Well, the inverse R prime is I. Again, they're inverses. So the whole thing is inverse R times Q prime times B. Okay, it suppressed it because I put the comment symbol there. So but that's all it is. So now if I want to solve this, if I want to find the least squares, I just need the inverse of R, Q prime B. Q prime B is going to go so fast. Let's do Q prime B. So let's go right side. Right side equals Q prime times B. Okay, and now it's ready to solve by back substitution. My XLS is going to be R inverse times right side. But I could also just solve, I could think of this also as, if I do the comment thing again, where is it? This is also, if I multiply both sides by R, I also have R XLS must be equal to right side. So I could just solve this. So let's see what we get. I'm just going to say right side and divide by R, and we should get the same. Wait a second, what did I do? XLS. Oh, I didn't put the right. Sorry. What? RXLS right side. What did I do? Q transpose B, the right side. We have XLS plus. Let's try it another way. What if we just skip that last step and just try to put in inverse R? So in other words, I want to just check that XLS is inverse R times, I wonder if times B. Yeah, there it is. I don't know what I did. But I don't really want to figure it out now. Anyway, I have a feeling most of you are probably tired now from this. I mainly wanted to give you an idea how to do different things: inverse, multiplying, adding, how to access certain rows and columns. I think we covered most of it with this one example. I wanted to do stuff with determinants too, but I do think the video is getting pretty long now. So let's stop now, and I will do this again for determinant and eigenvalues. I know there's stuff in here that should be edited out. I'm not going to edit anything out. So just use your mouse and move the cursor along if you want to get to a different part. Don't have time for film work. This is just for you in Math 130 fall. Wait, is it fall? Yeah, fall 2020. All right, thanks. And I'm going to stop sharing. If you have any questions, feel free to email me. I am going to stop recording now.